Okay, when you read the table, the potentials table, the table is written for E naught reduced. So all the reactions, all the half reactions are written in a reduction format. Now, the magnitude of the potential, well, it's just like the periodic table, right? What about the atomic mass? There must be a standard based on, so for the mass, it's based on carbon. So here the potential is based on this particular reaction, and call that exactly 0. So there's a reduction reaction, exactly 0. Then for half reactions, they can be either more positive than 0, or they can be negative, right? Because of 0. Positive, negative. For example, this reaction then is positive, okay, positive 1.51. And then for this half reaction, then it's negative. So you have a whole bunch of negative, a whole bunch of positive half reactions. Now, here is some good knowledge to learn. Now, you just look at all the reactants associated with the reduction half reaction, just like this. So looking at this chemical compared to this chemical to this chemical. Okay? So the higher the plus, the more positive, the stronger the oxidizing agent. The more positive, the stronger. Okay? Then of course this one is the weakest. So this is good knowledge, right? So once you have a jar of chemical, then you can tell, relatively speaking, whether it's a strong or weak oxidizing agent. Yeah?
Did you say the positive voltage means the spontaneous reaction?
Not yet.
This is not the
yet.
same
This is just half reaction.
So that doesn't apply here?
Not yet. The E overall must be plus. Right now it's just half reaction. Each one is half reaction. So electron, electron, electron.
Okay.
No spontaneous reaction yet. Okay? But now by looking at just the table, then you can tell the relative oxidizing strength of the chemical. Okay? And this is common sense that this guy is a strong oxidizing agent. Okay? So if you have a nickel chloride, then you know you cannot oxidize anything, right? Because such a low value. Now, if you look at these chemicals, so for this up here, then you are looking at reducing agent opposite to that. So now it's opposite, right? Opposite. This guy is the strongest reducing agent of the three. Okay, so you're looking at the opposite trend here. Okay, so don't get confused when you look at something by the entire equation. Rather, you're going to zoom in to look at just one particular chemical. So if in case of exam question, I give you a real chemical. Either it's a nickel chloride or it's a nickel metal. So if I say nickel metal, is it a strong oxidizing agent? Justified. Right? Then you know that, no way, it is a strong reducing agent because of that. Okay?
So can you look at the values and determine that? So if it's negative, then you get.
That's right. That's right. Yeah, you will be provided with the E naught reduction. Okay, so your attempt is to make a spontaneous reaction. Let's say you are constructing a yeast cell rather than direct mixing. So we will address the point in the future. Direct mixing of two chemicals versus when they are separated as a galvanic cell. Okay. So let's say you're going to make that with iron chemical and zinc chemical. So how would you design a spontaneous cell? So I might give you just like that, from iron chemical and zinc chemical, and give me a workable E cell. Okay, so now for iron, you can have 2+, you can have 3+, you can have iron metal, pure metal. The 3 possibility, iron 1+ is rare. So for zinc, then you have the metal, you have the 2+, so this would be your possibilities. So let's say you end up with, not consider the iron metal because of, some reason you don't have iron available. So this would be the picture you're going to draw, okay, and predict whether there's a potential here or not. So this is only your preliminary. So now to prove the feasibility, whether it's spontaneous or not. Then to reveal, then so in case reaction goes, then you're going to have the reduction here. So the first step is to write the higher positive potential first. So this equation gives you a value, and this equation also reduction gives you a value. So first step is the more positive is written first, and then followed by the lower positive or negative. So the two equations will be written like that. Okay, step number 2 is just combine the two. That means simply subtract, because this is reduction, this is also reduction, right? Both of them are reduction. So when you combine, it's actually, you need to switch the lower one into oxidation. So the minus would be in front, so this one is switched into oxidation. Then the third step is balance the number of electron transfer, because this is 2 electrons. So the top one is going to be multiplied by 2 all through. But cautious, this guy, the potential will not be multiplied by 2. Very important, okay? Memorize that, write that down in your notes for review. So this one is not multiplied by 2. So now you simply subtract, then you will end up with that, yes?
Okay, so you take the more negative voltage, right? And that is your oxidation, so then you flip that?
Well, the guideline, the step is simply write whatever this equation with a lower positive potential. Okay, just that this one, originally the reduction potential is in minus, but it could be hypothetically a plus 0.123. It's still lower than this one. If this one was plus 0.123, then it's still written below. Okay? While the minus, of course, is tremendously lower than that. Okay? More negative.
I don't understand. So because it's more negative, it means it's going to be going through oxidation, so that's why you flip the values, so then that becomes positive. And
Well, remember your hydrogen is 0 here. Okay, then this guy is plus 0.001. And the other guy is going to be minus 0.763. So the step simply calls for, to assist you how to determine spontaneous overall reaction. It's simply first you write between the two, write the one with a higher positive first. Okay, so that is higher positive. So this one next. While this one could be some, let's see, it could be a half reaction here. Let's say it's a plus 0.123. Then this one is still lower than that, and therefore no difference. So this one is going to be written below. Okay? Or another one is even more minus 0.96. Then this one you still write below. Okay? So it becomes a minus.
No, I understand that you write it right below, but in terms of like getting the overall value, that's what I'm not sure of. So,
Oh, that's coming up next.
okay.
Jessica?
So Dr. You said that if you multiply the equation by any number, you multiply the.
That's correct.
the
So whatever to balance the number of electron here, nothing to do with the potential.
So that's gonna stay the same.
That's right. That's right. So now, step number 3 will be, let's see, step number 2, that is you're going to combine the two half reactions, right? So combine, meaning you're going to switch the lower one into oxidation. So you put a minus sign in front. Okay, so minus, that means switch, right? So this one becomes reactant, and this one becomes product. So now this one minus is the sum of the two. So this becomes a plus, and therefore this reaction is spontaneous. If this was minus, then this reaction is not spontaneous, right? So plus minus is a plus. Okay, so
In this case, we're adjusting the second equation to make it oxidized, right?
that's right.
Or reduced, that is.
Oxidation.
Okay.
You
So
cannot have two
are you
half
adding-
reaction to a reduction.
once you adjust the equations, are you just adding the two values to get your overall?
If you pre-adjust,
Okay.
you pre-adjust, you
once you adjust
predetermine this
everything.
is oxidation,
Once you adjust, then you add the
then you
values.
just add.
Okay.
But in this case, for convenience, this is reduction, this is also reduction, and it will work because this one is higher positive than this one. Okay, then so.
No, I got that. I just was thrown off because you have subtract over there. So
That's right. That's right. So you will need to subtract the reduction to make it oxidation. So this one will switch. So the sum of the two is plus 1.534. Yes.
Wait, you said you could have two reduction reactions and it could be spontaneous, but you can
No.
have two oxidized?
No,
You didn't say that?
no, I did not say that.
Okay,
I said-
fine.
I said you cannot have two reduction reactions. You must need to switch one of the two. So just that the steps here, if you follow properly, automatically you're going to switch the bottom one. Going to be the oxidation because the higher number is going to subtract the lower number.